Okay, so this is our final weeks, the last week of class, and there are 2 lectures. We have covered everything that is relevant for finals. So whatever we cover now is not part of the finals, but you will see how this is actually applied, everything we learned in the sustainable aspect of this class. Okay, so these are more of examples so that you can see what you learned can be improved in your own lifetime if you work in the sector. And second half of the class will have final practice problems. So I'll give you one long questions to work here with your friends together. I'll be here. So it's more like imagine that's a final questions. How you react, how do you work together, how to work. So I'll give one example question every day, every class. We have 2 classes remaining. Today I have 2 questions. Next class we have 1 more question, or if we don't cover the question. So you have at least practice for 3 long questions in your finals. And we'll have we have quiz on December 1st. So that will also help you prepare for the short question in the finals. Okay. Just want to announce that homework 5 solutions on CCLE, so you can check that, compare with your solution. But we are now trying to wrap up everything and release your grade for all of, including midterms, which I'm now finalizing on your. You'll see that if not tonight, definitely by tomorrow noon when you check, you'll see all those. This week, I suggest that every day we are releasing some grades for your homework grades and all that. You may see that some of your grades are missing. That's because if you send me homework solutions, those are not graded. I'm grading now. Okay, those are sent to you, upload on Campusware or not Campusware, on Gradescope. Those are graded directly by the TAs, and so that means now those will be released very quickly. Other ones I'm just have to do it manually. So send me email by Thursday night. If you don't see some of your grade, send me email. That way I can update that just in case I missed it. And as you just again reiterate that week 6 to week 9, everything covers is part of final. This week, whatever we cover is not part of the finals, but we'll have example question for the finals so that you can see those. Homework 6, again, I just want to mention that homework 6, do submit, because that's still your grade. It's just I'm not grading them. That means you just submit and I see that you have worked out, you will get full credits irrespective of your answers. I just want you to give it effort. Okay, and there are only 3 questions. Those are short, not very long questions. You just plug the right formula so that this will help you prepare for your finals. Okay, so I don't want you to not do it, because I could have just take the homework out, but I want to try that. Okay, so no extension, because I don't expect you to work everything in correct answers. And so don't ask for extension, because I'll release that solution on Thursday night. In fact, it is already released. It's just it will activate the release at that time. I just set it to open it up at that time. So I uploaded it. You just can't see it until that time. Homework 6, one of the question was related to removal of pollutant from contaminated water or contaminated groundwater using activated tank. Okay, so this is also part of a long question in final, because you have, I'll get to that. There are 3 possible long questions. One is from drinking water, one is from waste management, one is from wastewater treatment plants. There is no long question on air quality. Okay, so these are the 3 possible long questions, and this is one of the questions that you have practiced for the for your homework. So I'll explain that a little bit more so that you can at least understand the concept and give it a try. And next week we'll have another example so that you have practice for these questions. So in this question, this is the only equation you need. Okay, and there is another equation you're already familiar with. I'll just mass balance equation. I'll put it there. Well, a lot of times, what happens is in those problems, you'll be given a contaminated water that you have to treat certain volume of water by passing through a filter. And that filter has certain materials, which could be activated carbon, which could be any other things. And these equations will predict how much of the pollutants will adsorb on the activated carbon. So this equation, as you see, there are three terms here. Q is concentration of pollutants, concentration on solid after adsorption. So when you pass the pollutant through the system, it will adsorb certain amount, and then that's basically says that's the concentration. And C is concentrations in water after adsorption. Okay. This is basically your treatment goal. What's the pollutant level you wanted it after adsorption? Kd is a constant that's normally given to you. That's basically, you know what that means. In your groundwater problems, you know Kd is FOC times KOC. It could be the same thing. Okay, it's just the adsorption coefficient determined by the property of pollutants as well as property of materials. So this is a linear form. This is what you use for retardation factor. But when you use high concentration of pollutants, the amount of pollutant that can adsorb on activated carbon is limited, because over time things will accumulate. So in that context, this is not form a linear equation. This look like same thing, but there is the concentration term has a factor 1/n. That's just a constant. What it means that the difference between those, if you keep adding, if you plot those two equations, what you'll see that if you keep increasing the contaminant concentration in water, more and more pollutant, equivalent amount of pollutant will adsorb on the solid. So you will see a equation that look like this. The slope is Kd. Okay, that's the linear equations. However, for nonlinear equations, yes, I'm going to write it in a green. What you see is that it's going to look like this. Okay, what it means that if you keep adding more pollutants in water, your concentration after a point, you will not adsorb onto your solid because they are being saturated. There are too much pollutants on activated carbon. It doesn't have enough capacity. So it's just going to saturate at some point. So this is non-linear. So this one, this is linear. This is non-linear. And it turns out the activated carbon tank has this pHr. So this is the equation given. So if that equation is always given, that means you Kf and N given, or 1/n given. So you don't have to derive anything for that. What this will tell you, and this C is the concentration of contaminants that you after treatment. So this basically usually given in certain way in that questions. For instance, you will say you have to treat the groundwater to 99% removal. That means whatever your input, the C output has to be 1% of input. So this C is usually given because you know what's the treatment goal. Okay, what's the concentrations. So if you know this C, this equation you can use to see how much pollutant adsorb on activated carbon. Okay, so this is the Q we will calculate in your example question. Okay. So that's basically you calculate Q, which will be milligram of pollutants or whatever the pollutant, microgram or milligram of pollutant, gram or kilogram of activated carbon. Okay. Or another way to say this is whatever solid you use inside this. So that means this will tell you how much pollutant was the capacity of that activated carbon tank. That means if you take 1 kilogram of pollutant, you can remove only certain amount of pollutant. And in that question, it asks how much pollutants how much activated carbon you need. Okay, so this is the capacity. That means you have to calculate how much pollutant to be removed. Okay, so this is concentration. This is a concentration term. So if you want to use, so that's basically mass of pollutant divided mass of activated carbon. Okay, so this is activated carbon. And usually you are asked to calculate SC. That means you have to multiply Q times MP. Okay. And what is MP? MP is the total amount of pollutant you can remove from the system. And how do you know that one? Usually what you are given is what's the concentration of pollutants in the contaminated water. What is given is C in. Okay, so this is the activated carbon. So imagine that this is activated carbon. You are given C in. You are also given C out, or it basically says C out in certain way. It says 99% removal. That means only 1% of C in will be in the C out. Okay, so whatever way you can, this is given in certain way. So anyway, you are given C in because that's the concentration of pollutant in water. C out is given in a certain way. So you know this number. That means you know how much pollutants can be removed, and also you're given Q, how much of water you're going to treat per day. So based on this, the mass balance equation, you can calculate how much pollutants are removed in activated carbon tank, because you know what is out, what is in. The difference must be what is removed in the system, and that has to go to the activated carbon. So that means MSC or MP, mass of pollutant removed, has to be mass of pollutant coming in minus mass of pollutant going out. And you know from mass balance equation that will be QC in minus QC out. Okay. A lot of times, so that's basically QC in minus C out. And a lot of times it doesn't say Q, it says that you have to treat 10 million gallon of water per day, which is basically a flow rate. So that's Q equal to T times, this is M dot, means how much amount of water that, or amount of pollutant removed per day. Okay, there is a time factor there. So another is if you say per day, how much is treated. So this is basically another way to write is C in minus C out times volume equal to mass of pollutant removed. Okay, the volume of water treated per day. So this B has a time factor. Okay, how much volume of water you treat per day. Then you don't really account for that. So normally the one I gave you it says per day. Okay, so that means you just account for how much water treated per day. So if you put that value, you get amount of activated carbons you have to use per day. Okay. And then the second half of the question is how many tanks you need. Okay, that's basically how many tanks can fill this activated carbon. That's just basically it's like a volume of activated carbon. So how many tanks you need? Number of tank. Okay, you need is basically the volume of tank. If you calculate volume of activated carbon divided volume of tank, so volume of activated carbon divided by volume of each tank. Okay, so basically you're filling in, okay, to the nearest number. So let's say the answer is 3.3. You really can't do 3.3 tank. You have to make it 4. Okay. So now that means volume of tank is given because that's given usually 55 gallon tank. So the volume is given. This is given. This you have to calculate. Okay. How do you calculate volume of activated carbon? All you know is mass of activated carbon. That means you just have to know the density, packing density. Okay. So volume of activated carbon by volume of tank. This is usually 55 gallon. Okay. I would say this is greater than this. Okay. Greater than equal to. The reason is if you get the answer 3.2, you cannot say I need 3.2 tank. You need 4 tank. Okay. Because you can break the tank. There has to be nearest number higher than that. Volume of activated carbon is basically mass of activated carbon that you calculate times density, packing density. Packing density same as bulk density, okay, which is here. So again, this is for soil, but if you write this for activated carbon, this is given. So this is usually given. So you calculate that. So that's how you can solve that question. Okay. So try that example question, not example, the homework question that is given to you. If you know how to solve it, that's exactly how you can do the final. Okay. Question. All right. So in the second half of this class, we'll solve some example questions from finals so that we know how to, again, the same process. We already did one question. This is one question in the final. And you have practice for the homework, and I can give you another question if you need. Okay. All right. So let me write what's the main topic in this week. It's written here, but it's not visible. Okay. So now what you learned so far, let me, if I would paraphrase it, what we have done so far. In the very first week, you learn about chemistry. Okay, chemistry, how to write units, how to convert one unit to another, because a lot of times we deal with environment and environmental pollutants. So you have to know how to measure those environmental pollutants, estimate their mass. That's why you need that first week of class. In the second week or third week, you learn about biology, little bit of chemistry, risk and all that, so that you know why you need to design the system, because we need plants, we need microorganisms, so you have to have some understanding of that. Then we get to mass balance. Mass balance means any system you want to see, design a system which is sustainable, you got to have an idea of how to measure total pollutants or mass coming in versus out, so that you know what's being consumed, what is being used, how much waste is produced. That's the whole reason for mass balance equations. Then we apply mass balance equations for specific reactors, because reactors are different treatment technology that you will use in futures. And those reactor could be pond, it could be lake, it could be rivers, it could be anything that any environmental system. Those are also a reactor. So now that you learn all the basic aspect of it, then we went on to solve some question on surface water. Surface water means, anything move on the surface, that could be lake, could be pond. So those are the things we solve it, but those are part of the midterms. In the very specific, so this is where we finish then we go to groundwater. We solve question on groundwater problems. So how far the contaminants will move, how do you know how much plume is coming at what directions, and then how do you capture those plume. Okay, so we talk about those are the two natural systems in those, and then there are BOD issues, the rivers, how much waste is discharged, and how to determine how much BOD will be at certain point. So those are all we learn in the before midterms, and those are not going to be part of the finals. Then we start working on specific treatment design. The very first thing we learn is drinking water treatments. That's the week 6. If you go to the week 6, this is what we learn. Drinking water treatments. So what we learn, the most thing is drinking water treatment. There are 3 types of things we learn. One is settling. If you remove particulates, you just design this clarifier and you learn how to use Stokes' law to calculate how much is being removed. Then you learn very specific aspect of drinking water is hardness removal, and that's a one long question. That was one question in your last homework. That's going to be a very critical question in your final. Okay, so if you know how to solve the homework question, there is no way you cannot solve that question in the final, because it's the exact same question, just the number will be given different. But there is no way I can ask the hardness question any harder than what is already in the homework. Okay, it's just tedious. That means it takes some time for you to get all the numbers. And as I said, I don't really check. I mean, I see the numbers what you have, but I don't really take point off for a wrong numbers as long as your approach is right. Because I expect that sometimes you miss, calculator or whatever things, because I can always give you full credit even you just write the equation, put all the numbers. So I'm not really looking forward to that final answers. But if you miss, for instance, a conversion units, those are critical errors. So I take some point off, very small fractions, but you have to check those. So in drinking water, you learn about hardness. So there will be one long question on the drinking water treatments on hardness. So do this question very seriously. Then in week 7, we actually have we work on wastewater treatment design. Okay, so in wastewater treatments, you also went back to the same gravitational settling clarifier design. Okay, but now in wastewater, you use clarifier mass balance as opposed to calculating the settling velocity. You can calculate settling velocity based on the mass balance equations. Okay, so that means you have to also think of settling mass balance. Okay, this is also in the example questions as well as in your homework. Then we have also the main question, long question on wastewater treatment plants is combination of mass balance and secondary water treatments or activated sludge process. So aeration tank, okay, aeration tank, activated, let's go right here, activated sludge. So those are things you learn. So this is basically going to be one question, okay, which has settling tank, the secondary treatments. Then we also learn solid waste management in 1 or 2 classes, landfill, all that stuff, but landfill is not part of a long question. This is mostly short question or quiz questions. What you learn in the solid waste management is more about treatment of groundwater using activated carbon tank. Okay, so that's the things that I just explained that example. Okay, so this is homework 6. We just explained, okay, carbon adsorption. So that's the same thing here. Okay, and then we also have air pollutions in the week 9, but this will be mostly short questions. Okay, because you just have to know how to write the equations and plug the value to answer conceptually as well as numerically. So that's your finals. Okay, basically this is everything you need to know. But if you see, what this class mostly is about is sustainable design. So nowhere in the entire class I talk about sustainability, even though it's already integrated part of it. The reason is, if you see the 3 pillars of sustainability, these are 3 factors you have to account for. First is social. You can design whatever you want, but it has to be used by people. It has to be it has to be people friendly. It doesn't disrupt our way of life. Okay. So the social aspect is important. For instance, you can design a road, but only few people drive, not 90% of the people don't drive. For instance, you can design a road for electric car. Yes, the question was, does that mean the final covers only 5 or 6? Yes. You have 2 questions. In fact, yes, you're right. So the social aspect is important. That means when you design a road, it has to be inclusive. It has to be used by everybody else, not just the rich or poor, everybody else. But right now, if you see, our roads are designed in a way that people with car takes 90% of the road space. Okay, if you see of who use those cars, how many roads are designed for multi-purpose, and many people may not have car, even may not use car every day. So that means if you see, anytime you design in a sustainable city, which is today's class about, you have to think of social aspect of it. And the second one is environmental. In fact, the entire class was this. Okay? Everything you do is environmental, engineering, treatments, all that. So we really don't emphasize it, but if you remove this one, there is no sustainability. So everything we cover, it's kind of redundant to say that environmental engineering is part of sustainability. Without environmental engineering, there is no sustainability. Without environment, not just environmental engineering, environmental science, everything included. So we don't really talk about it because we say that, no, this is part of us. Okay, so we don't have to write that. The last one is economics. So these two, I didn't really cover it in this class. In fact, those are the things you'll learn in the following, in the next quarter. When I talk about waste management, we talk about economics of waste management, which is feasible, which is not. In the following class, green infrastructure design, you will also talk about cost of design. I really never included cost of design in any of your questions. So these two will be mostly covered in the other class, but I just want to give highlights in this class so that you know how this is applied. Okay, so for instance, economics, one example. If you have read the news, in some point, California imposed or passed a law, not law yet, advisory limit for PFAS. PFAS is found most of the places. It's a highly, it can cause cancer, it can cause birth defect. The concentration that EPA approved is actually now 1 parts per trillion. When you think of trillion, it's a big number, right? Imagine $1. You spread lots of trillion coin on a field. I don't know how many football field. And then you put 1 coin of those as a gold. And you have to find that one. That's exactly the numbers you are looking for. So you have to find the pollutant in water as that low concentration level. Because it's so toxic, or at least the effect, they have human trials and they found that actually it caused cancer at very low level. So that's the reason. Now, imagine the cost of treatment. If everybody treat all the pollutants, all the PFAS ever present in US, the cost will be $500 trillion. You will not have that much money. Okay, so you have to think of that now. You can create all these rules and all that possibility, but you have to also think of, do we have that even that money we have to do it. So all the times when you design a system, you also look at the economics aspect, not just the science. What is feasible? So that's why many of the environmental solutions, it's not about technology limitation, it's the economic limitation. It's also public acceptance limitations. So these are there's a term just to say that what is sustainability. That means you have to use the resource without depleting it for our future generations. Sustainable development, which basically integrates that idea that you can have the development, like you can create a city, but you can't deplete the resource around it. For instance, Los Angeles, because it is expanding, imagine the cost of water. Imagine what's the water available at that place. It's all depleted. We can't continue doing that. That's why they're thinking of how to expand city for next 50 years or 100 years without really depleting the resource. We don't have even, we borrow the resource from future. And sustainable engineering is basically how we design that, what we are doing. So I'm going to give you examples. We all, in future, we are going to drive electric car, right? You see a lot more Tesla on the market than before it used to be. It's no longer like few people have it now. I can see every time I drive, I see how many Tesla is there. Many more common. In future, in fact, in next 10 years, you'll see more electric car than the gasoline car, because it just it become more economics and all that. So this is just an example. If you just do a little bit changes, electric car is lighter than the things that you use in normal gasoline car. Just by lowering the weight, you are consuming less fuel. Okay, for one thing you can do incremental improvement is by making your car lighter and lighter. That's why you see, when you drive cars, some say that carbon fiber material, all that stuff. The reason is just to decrease the light, make it lighter and also increase the strength. Then you can also replace engine with electric engine as opposed to gasoline. So that, and then you can also change the shape of the car or design the car so that aerodynamic resistance is lower. So that will also emit less carbon dioxide. Also, it will improve your energy efficiency. Then the last thing is you can also think of what kind of, you design electric car, but you have to also account for where you are going to recharge your electricity. So you have to create infrastructures to recharge the battery. So all that is also part of your sustainable development. So when you think of just replacing car with another car, is not the infrastructures are not designed for that. So you have to account for the whole thing and see how you can improve that, other benefits, not just carbon dioxide. One thing that you never heard from most of the people is what happens to the car after the electric car, the consequence of electric car. Imagine everybody start using it. There's so much battery. How do you manage those? Because that's the biggest waste. Unlike gasoline, you burn it, it's all gone. Atmosphere, carbon dioxide. In fact, the whole point of electric car is reducing the carbon dioxide signature. And it has engine oil, all that stuff. It is, the gasoline, it can be treated. So we all know that electric car will decrease the deficit for carbon dioxide after it is being used. This doesn't account for the production most of the time, or maybe it does because it says life cycle. That means it will include the production, manufacture, and all that. So it does reduce. But this whole thing is unsustainable unless you know how to manage the battery, spent battery. You cannot just dispose them in landfill. You have to recycle it. So the whole process of electric car has to go through this process of remove the battery, have a system to separate the battery elements from hazardous materials or things that you can be used. Then you repurpose it and take the hazard out of it, and then you can send to another place and create a new battery out of the old materials, so that you have less and less waste. You cannot just dump the entire battery into landfill, which is the case in many places. So this industry is going to be developed very rapidly if more people are using electric car. So as you see, even though it's not as simple as saying that this electric car is a good replacement unless you account for everything associated with it. Okay. Another example, water for a city, for instance, Los Angeles. Think of that. 100 years ago, or 150 or 200 years ago, Los Angeles didn't have enough people. When the native Indians were here, then after that, they found gold. That's how things, mining, all those things. California got a lot of people because of the gold mining. That's why it's called Golden State. And Los Angeles particularly attract more people for a different reason, if you see history. But eventually, the port of Los Angeles is the reason a lot of people live here, because the good that you can get. But this is a dry city. This is middle of it's like Las Vegas. Naturally you don't have enough water. So as the city expand, they start finding water from different places. So as you can see, these are 3 different main regions. Los Angeles aqueducts, very small portion is groundwater. Then you have this design this big aqueduct or the canals to collect water from Northern California, miles and miles long. Then also you got some water from Colorado rivers, or I think majority of the water. So as you can see, we keep exporting water from somewhere else. And there are excess water before, but now Colorado river would not have enough water because of climate change, because of other things. That it's not just the river belongs to California. You know, this is shared by many other states, Arizona and other places, including Mexico. Okay, so that means there is a California that water rights that limit how much water you can withdraw from Colorado rivers. And nature also is changing, or the climate is changing. That means you have less and less water available in a predictable manner. That means you have to think of that aspect. So you cannot design Los Angeles expansion without accounting for water. So that means this whole city will collapse if you do not think of life cycle assessment of water, how to get those extra water. So the next class in the spring quarter, I teach a class called green infrastructure. That's basically how to design these infrastructures, so like roads, water treatments, so that you can have enough water in the big cities. Okay, mostly stormwater for specific. So another thing to think about is also paper towels. Whether you should use dry. If you see, go to restroom, you have paper towel versus the dryers. Okay, so which one is more sustainable? So all these things can do calculations. Biofuel. You know that many, like 10 years ago, so there was suddenly a lot of rush for corn, because people thought that they are now going to use corn will be the next gasoline. So you don't have to dig oil. You can just grow oil, which is basically corn. But then later they found out, because corn productions, you kind of destroy the ecosystem in a way, because it's not very efficient. That means it also take the same space that used to be food. Now you don't have enough food for that. And then they realize all the efficiency, everything is not economically sustainable. So the whole corn thing as a fuel is not environmental sustainable way. And you can read more about that. And so this is now the new way of thinking. So these are the different way you can think. What is the traditional method? What's the social indicator? What's the environmental indicators? What are the economic indicators that you can use to see whether your system is very efficient in long terms or not? So again, I'm not going details about it, just so that you know. Okay. But bottom line, any new design you introduce, you have to think of the waste, because that's the end product. A lot of times people say, I have excellent technology, I can, here is the things, but people don't account for what happens after this is being used. What's the waste is produced? And so sustainable aspect of that means you have to recycle the waste. You have to reuse the waste, recover the waste, resource out of the waste. So as I said, CEE154 is more about solid waste and recovery of waste, resource out of solid waste. And the CEE159, which I teach on in spring, which is mostly about stormwater, because stormwater's design is related to the infrastructure. For instance, any roads, any building you design has to be associated with harvesting stormwater, as well as lowering the energy cost, because this green infrastructure can lower the energy cost of the city, as well as your building heating bills, as well as cooling bills. So CEE159 again is offered in a CEE164 is next quarter. I know that many of you enrolled. It has, I think, 170 student maximum. And it used to be 60, and I changed to 70, so that if many of you missed, you have at least 10 more seats. Green infrastructure, the prerequisite is 153, so that means all of you are official, you can take that. And many of the questions in this class is also very related to, or similar long question as this class. Okay, so that means you are kind of know already how to answer 50% of the quiz, 50% of the midterms. There is no final in this class. Same way, it's a project-oriented class. You'll design the projects as a team. So that's more like applicable for your jobs. So what is green infrastructures? If you see, just to give idea, This is what Los Angeles was 200, 300 years ago. Natural land. There is no building, no parking, no roads. So whatever rains you receive, most of them goes to infiltrations. Some of them become shallow infiltrations, so replenish groundwater. And very little as a runoff, means you don't see flooding. And many of them are evaporations. But imagine what you do. You start building homes, you start building roads and all that. What you are doing is you are introducing green impervious surface. Impervious surface means any water that comes in will not have the ability to get inside. So if you see over what happens at the end is you have very little infiltration. So that means the groundwater that you very much need for drinking water is gone. Okay. And in Los Angeles it's even worse, because normally you limit groundwater infiltrations, you deplete the groundwater because you are pumping a lot. And because you are pumping groundwater, it's a coastal city, all the ocean water is coming in. So now any groundwater you have is becoming salty and salty. So that means it's becoming less and less usable. So not only you are depleting the groundwater, you are also decreasing its quality. And then the another big part of the issue is that 55% runoff. Before it used to be only 10%. Now you have so much more water on the surface moving at very high speed. So that means you'll have lots of flooding. And because of that flooding, you see this Bioreactor Creek and Los Angeles River, they are designed to remove those flooding. Okay. And so they were created to reduce flooding in Los Angeles. And those designs are, as you can see, all you are doing is moving the waste from one place to ocean. Those waste are resource. So you can't really keep dumping all those things. So you have to reuse it when you don't have enough water. That's the role of green infrastructures, reducing the runoff, replenishing the groundwater, and treat them so that you can reuse. So that means all you are doing is bringing some of the green space back into the big cities. So that means you design your parking lot such a way that water will infiltrate. You design your rooftop such a way that it can hold that rainwater and infiltrate into ground, so you can reuse it. And when you do that, you can also lower your electricity bill because cool your house. So this is green roof. This is a parking structures, how it is designed, as you can see. This is a rainwater harvesting tank. So that means any water comes on the roof will be collected in this tank. This is just another way to say that the roadside, you can design this rain garden, they say, because basically you don't apply any water. All the water comes from the, you see this is the roadside, you have a curb cut. You can see outside now, any place you drive, you see this curb cut. Those because, the stormwater will get into this area. That way, it can be treated inside and naturally infiltrated into ground. These are things you see all the places. As you see again here, there is a curb cut here, our locations. So what will get inside that through those processes. So this is a curb cut. This is a curb cut. And then you see this is bioswale. That's basically a location that you see. These are all part of the design. This will help infiltration of stormwater into ground. So this is why it is called green infrastructure, not gray infrastructure. Even though it uses cement, all that, it also allows the nature to come in and have that treatment. So this LA River, you see a perfect example of how not to manage stormwater. Okay, so now that's why they are reinventing, they are replacing those concrete in LA River so that naturally it will be a natural river so that there is some treatment. So just to show that the future stormwater treatments, as you see, this is the past. This is what happens in LA. Amount of water comes in for different use. Recycled water is less than 1%. But in future, that's going to change. You will use more and more recycled water. You will use some more stormwater. And you are going to locally produce many other for different reasons. So it's not going to change completely that all the water is going to be locally harvested, but at least you are increasing with time by 2035. And then it's going to increase by 2050, the percentage will be more and more. So these green infrastructures, as you see, this is not just for water treatment. It has many other benefits, social benefit. For instance, think of this. You are biking on a bike path with a lot of trees. You'll feel happier. You have more connection with nature. There are many other aspects of it. It's not just the stormwater treatment. So you can see all these things later. Just again, another ecosystem, some examples. I don't want to treat. And this is one thing I want to mention. This is my research. This is what I do as a research, how to design this, build them in a way from materials that is sustainable. For instance, this is from any junkyard you see. Now, junkyard, you have all these iron, rusted iron. We take them and create a materials that can treat stormwater. This is any bio waste. Your garden waste can be converted to this biochar and be used in those filters to treat stormwater. So you learn all those in those classes. And again, another examples, California Transportation Agency funding us to redesign the roadside so that you can treat the stormwater right there, and you can make the road more effective for multi-purpose use. And then in the next class, CEE154, you learn. I'm just going to next quarter. You learn more about how to produce energy, do calculation, all that. We learned this one. We didn't really cover this one. How you can take the sludge, the wastewater sludge, and use a different processes where you can directly harvest energy. Replace all that you learn in the wastewater treatment plant. For instance, aeration tank, clarifier. Instead of doing that, all you do is a deep membrane, which is here. Okay, just put the membrane. That membrane will filter water, but it has other microorganisms which will digest it. So this is called anaerobic membrane bioreactor. This will replace the entire thing, all the three things into that one little space. So all those design you learn in the next class, next quarter. So again, I don't want to mention that, just to show that these are the anaerobic digestion is a treatment technology. That's how you can process all your food waste. I'm not going to show any other things. Just want to example. You can change directly solid waste to energy by just burning it, but it has environmental consequence like carbon dioxide, toxic gas, which is not usable. But you can use something like pyrolysis, where you are not really burning all into carbon dioxide, but burning without oxygen, so that the material carbon become a filter material. That's how you make biochars or activated carbon. Rest of them, all the biogas that emitted, you can recycle them, create fuel. Then also you learn how to design the landfill, or at least in principle. So these are the different ways you can think of how to manage all these waste. So this is again as an example, why we talk about all this is when you think of big city design or expanding Los Angeles, you have to think of how to manage waste so that you can recover those waste materials. You can produce energy so that you can supply electricity to the expanding populations. You can also harvest water locally. And all these things has to be including, it has to address the social aspect of it. That means any of those designs should not favor just one group of people in cities. It should be equitable. It should be available for all publics, not just one. So when you design road, it has to be used by everybody, including biker, including person who walk, including person who drive electric car. Okay, so these are the future city design. And 2028 we have Olympic in LA, and they are going for that route. Okay, so that's why you see this metro is being designed, because more people will use it. Metro can be cheap enough for everybody to use. Okay, so that's all for the today's class as far as the materials. But in the second half, as I promised, we'll cover some questions about final. So stick around. Well, I'll give you questions. I'll a little bit talk about what's in the final and all that, and then we solve one question together here. Okay, so you'll come close to each other, create a team so that you can learn from each other. Okay, so we have 10-minute break. Let's meet at 105. Yes, CE159. It says that CE150 is a prerequisite. That's the old thing. That's not anymore. Okay. Yeah, there is no other prerequisite. Oh, I see. But you know what, that can you hear now? Let's see. Oh, I see. The reason is what you see on the iPad screen is not, iPad is not the receiver. This is the receiver. So I keep the audio from this screen, but maybe that is related to both. Okay, I'm glad that you guys, somebody mentioned that. Okay, so there are, again, to reiterate, there are three long questions and one short question. As you see, question one will have 10 short questions like here. And then there are three long questions, 2, 3, 4. So this is question number 2. This is question number 3. And question number 4 could be adsorption, carbon adsorption, like example question. Or usually it is now, as you can see in the last year final exam, you have air quality question as a long question. Okay, that could be also similar to that. But the question is here, one of them you have a choice. Okay, so these two, question 213 is definitely hardness question is there. You have to prepare for it. Same thing for wastewater treatment plant. In some year, I put carbon adsorption and air quality as a choice. So you have both two long questions given, but you choose whichever you comfortable. Okay, but there will be only one question on that. Okay, you don't solve both. And as you see, I just check on CCLE, your final exam time is 11:30 a.m. to 2:30 p.m. on Monday, December 6th. Okay, so what that means is I release the question at 11:30. Okay, because I have to because by syllabus I have to release it that time. There is no flexibility on that because some students they have finals in other day, but you have 48 hours, more than 48 hours to work on any time you want. Okay, within next 48 hours. So that means once I release on Monday, you have till Wednesday midnight to take the exam. Okay. So the reason I release on Monday is because that's the day is designated. So other students are taking classes. So I'll make sure that they can take the exam in the time that is given to them. Okay. And usually as you see, 11:30 to 2:30 is a three-hour exams. But I give 2 extra hours for you to, if you need that time. It's not really, this questionnaire set for 3-hour exam. Like imagine if you would have taken in their class, you would have done it in 3 hours. But because I take home, I give extra 2 hours because there is no circumstances. I don't want you guys to not do a question because time is a factor. Okay, so I don't want that to happen. That's why I don't give a 5-hour exams. I give 3-hour exams, but you have 2 extra hours just in case if you need it. Okay. So just again, a lot of times people get panicked. They say that 5 hours. I don't have that 5 hours. You don't need that. You need 3 hours. Okay. Yes.
So for 5 hours, when we click it, we automatically have that.
Yes. So the moment you open the question on grade scope, you have 5 hours from that time. Countdown begin from there. Okay. Of course, if you ask for CAE, through CAE extra time, those will be given automatically there too. Just think that practically you have enough time for this exam. And another thing I want to mention that the will grade final exam very quickly because I want you to see your solution before I release your grade. So after the final exam, that's why I put Monday, because let's say Thursday night we have the solution for everybody. We'll grade between Thursday and Friday. So by Friday around Friday night, you have your answer what you got in the final. And then if you see, we are giving another extra weeks to update your grades. So that means I'm going to wait for you to see or check whether your grades are correct or not, for not just for final, but for everything that you submitted, homework, everything else. So I'll not be giving you any grade until I get confirmation from you that you have, at least I have reflected all your homework, accounted for everything. So that means you have time to review your midterm answers too, just to see if just in case there is any difficulty or anybody's took unnecessarily point off. Okay. So you have, even up during the final, after the finals, check your grade scope. Okay. Check what you receive for your homework. Check your particularly check midterms and final. Those two are very critical because homework question you get mostly 100%. Okay, so check those two, see what grade you received, and review it just to make sure that you are not taking any point off. And request for regrade right on the grade scope. Okay. Any question? All right. Okay, so now the point is what you can do 12 from now on, because everything is done. Can't worry about that. The first thing is you have a quiz. Prepare for the quiz. Okay. That's the first thing. That's important things to do is prepare for the quiz material. So it will give you some perspective about the final questions. And quiz questions are very similar to the question already on the slides. So review those slides, take those concepts and do it. Okay. So those quizzes are one thing. Second is you have only 2 homework. One is you all just submitted, another homework which is still due, right? So do not submit homework. Okay. So that's I give you extension for all the homework except the one which is near to the exam. So that means the exam homework number 6, submit it on time. It's only evaluated for your submissions. So try it. I explained to you how to do it. We have given examples, so there is no reason for you not to do it, unless there is always medical issues. Those are, I understand. But you are here, so you got to do that one. Okay. And so homework 1 remaining, quiz is remaining. The significant portion, quiz is significant portion of your grade, so do not miss that quiz. Okay. You have again more than 24 hours to take the quiz once it's released, like other quizzes. And then we are reviewing final questions. So every day I'm solving one final question that will be very similar to your final, which is similar to your homework. I do not give any question that's very different from homework, partly because I train you the way you want to, the way it's supposed to be, and I test you for that. I don't test anything for you that is not covered in the class, or not. You will not see a question that doesn't relate to you. Like you have seen similar questions in examples or homework. So that's why it's important to practice your homework question, only 2 homework. So it's very easy to practice those. And again, come to ask question on campus, where if I didn't get to that, some other question I see, I'll answer that. Solve all the example questions given so that you get more practice. We'll also solve some practice question today. We'll just get to that quickly. Ask TA for support. We have office hour tomorrow. I can have another office hour on Friday if you need it. That's just basically answering any question. So I will have another office hour on Friday, just as the last moment questions. Or there is no TA here, so I'll ask the TA to come next class so that they can give you some tips. And again, the same thing, don't leave anything blank. The same way, don't submit you rather submit an incomplete homework than not submitting at all. Okay, because that's the same way. Just the deadline coming, just submit whatever you have. You can ask for extension, because always I give extension whenever you asked, unless, as I said, as part of the exams or solution is released. All right, so let's solve one question. This is exact similar question, was part of the last year finals or midterms, and I can see this is a question how you see. Okay, so I suggest that you who are sitting alone, they can find at least one person as a group, so that you can do together these answers, and we'll solve it. So this is, I'm going to read the question, so that in first 5 minutes we'll try to understand, interpret the questions, and then in next 5 minutes I'll tell you to write the equation that solve those questions, because that's the 50% of the solution. Write the right equations, everything else you plug the value, right? So that's the first thing I'll ask you, but let's read it together. You are asked to obtain 10 million gallons per day of groundwater with constituents given below. So this is the component given. You have given carbon dioxide, calcium, magnesium, sodium. Your alkalinity is given as calcium carbonate, sulfate, pH is given at 7.3. Except alkalinity, everything else is given as milligram per liter as constituent. Okay. So the first question, 2 point, is convert all concentration in milligram per liter as calcium carbonate. Draw the bar graph showing total non-carbonate hardness of water. So basically draw that graphs. Okay. First is conversion. So write the equations that will solve the conversion for different units here. So that I'll give you that 5 minutes, write those units. Okay, so write formula to convert units. Okay, for all those other things, carbon dioxide, everything else. B, estimate the concentration of calcium bicarbonate, magnesium bicarbonate, calcium sulfate, magnesium sulfate as milligram per liter of calcium carbonate. Based on the graph itself, you can calculate that. Okay. State your assumptions, show them on the bar graph above. So basically, this is the same question as previous one, but you will just draw the graphs and put the number. calculate the amount. So again, see this question, show them on the graph above. A lot of times people write it, but they don't show it in the graph. So read the question, all details. Okay, everything is asked, make sure to do it. Okay, even though you do it mathematically, there is a question, show them on the bar graph. Don't forget those little tips like this. I remember some students, they say, okay, I calculated, but it asks for so little bit points. Calculate the amount of lime required per day. Okay, write formula. Write the formula. So that's basically 50% of your grade. You just put the formula, write then all I know is you know what equation to use. Okay, and then rest is about plugging the value. So you get 50% just by writing the right formula. Okay. Calculate the amount of soda ash required per day. Right. Formula. Calculate the amount of solid. This is a concept question. If the pH of the groundwater increases, then would it be more or less expensive to treat groundwater? State your reason. Okay. So that's at the end, we'll discuss that. So at least we'll solve this question today. Okay, next time we'll solve another one. Okay, so you have 5 minutes to either solve alone or find a partner that you can talk with while you are writing all those. So you have 5 minutes, what I said here, write the formula to convert units, write the formula for calcium lime, write the formula for this, all that. Okay. Then, so you have 5 minutes. I'll get back to you in 5 minutes and we'll start solving. We'll pause the recording for 5 minutes. Okay, so before the break, so this is a typical hardness questions. This will be exact similar questions as your homework. Just have to understand concept. The only question that you see over here that was a little bit concept is the last one. Okay, so everything else is basically you should receive the whole full credits versus writing the right equations and plugging all the value. Okay, so before that I ask you, because the question I ask is how much convert all concentration in milligram per liter. Hold on, it says low battery in this one, so let me replace let's see, the microphone has low battery, so I'm going to pause again and just replace. Okay, so where is my pad? So molecular weight, so you have to change everything as milligram per liter as calcium carbonate. So equivalent per liter, so these formulas are equivalent per mole. For carbon dioxide is 2, for calcium is 2, magnesium 2 charge, sodium 1 charge, alkalinity is 1, sulfate 2 charge. That's how you can write. So the amount of part of molecular weight for equivalent weight is divided by, so 44 divided by 2 is 22. Why lime is not COOH? We'll get to that. There is a question on that. So this is basically 44 divided by 2. And this will be 20. This will be 24 divided by 2. So that's basically, I'm just going to write it. Solutions. 12. This is 12.15. This is 23, this is 61, this is 96 divided by 2, 46. So the answer in calcium carbonate is basically this, is a gram per equivalent for CaCO3 divided by gram per equivalent of weight for CO2. Okay. Now basically you're writing that. So this is going to be 6 milligram per liter times gram per equivalent of calcium carbonate is basically molecular weight of calcium carbonate is 100 and gram per equivalent is 2. So gram per equivalent for means for one equivalent, the amount of molecular weight is 50. Okay, so this is 50 divided by, for CO2, this is 22. So this answer is 13.6. For this one, same thing. The unit is calcium is given as 50 milligram. 50 divided by, for calcium is 20. So you are going to write 125. For magnesium, the concentration was given 20 milligram per liter. This is 50 for calcium carbonate, and the magnesium equivalent weight is 12.15. For sodium, this was 5 milligram per liter. Then 50 divided by equivalent weight of sodium is 23. It's going to be 10.9. This one, sulfate, is given is 94 times 50 divided by sulfate is 46. 46 or 48? 96 divided by 2 is 48. The answer would be 97.9. SCO3 is the same as alkalinity because the pH is 7.2. As pH equal to nearly 7 or 7.2, you can assume that this is same as. And this is given as alkalinity anyway, so you don't have to change it. It says that you have given as CaCO3, so you don't need to change it. Okay. So that's basically standard formula. All the time you can use the same formula and write all those things you need to. Only when I get the wrong answers, then I look for your steps. Okay. So if you just write without showing your steps, then as long as you are correct is fine. But if you don't write what you are doing and if you have a wrong answers, then I have no way to know why you got it wrong. Okay, so the next is show in the bar graph. Okay, so let's start doing it. So again, as I said, the way to draw this one is you have to see what is the total. Sodium plus, let's write calcium from magnesium. So 125 plus 82 plus 10 is how much? That's the total positive charge, right? So you have to write all the positive, all negative. So 125 plus 82 point, I'm just going to calculate here. So 125 plus 82 plus 10 will be nearly 200 something, right? So all I need is 250 range. So let's say this is 100, 200, 250. So this is small, it's 50 range, and this is 300, 200, 100. Okay, so first thing you have to do is calcium. How much is calcium? Calcium is 125. So this is 100, 150. So 125 is roughly here. So I'm going to draw 125 as calcium. So let's draw calcium. Okay. So this is up to 125. That take care of calcium. For magnesium, it's another 82.3. So 125 plus 82.3 will be a little bit more than 200, less than 210. So 250, 200, roughly here, let's say assume this is that one. So this is magnesium, or another, this is calcium. The total amount is 180, 125 plus 82.5. So it will be 200, this will be 200, let's see, 207.3 up to that. Then you have sodium, another 10.9. So this will be another little bit. Don't need to draw that one, but I just, let's say this is sodium. This will be sodium. Okay, we don't need sodium, okay, and because that's not part of how this thing. So this is 10 point. If you add 10.9 sodium, this one should be 280.18 point. Okay, 18.2. Okay. Okay. There is any question? Okay, I'll wait for that. Next is you have to draw the negative ions. Negative ion always start with SCO3 first. Okay, that's the carbonate hardness. So how much SCO3 you have? 120. So you just have to draw until 120. So let's draw that one. Let's choose a different color. Let's see. See this one. Okay, so 120. So this is 150. This is 125. So it will go a little bit less than that. Oh no, I'm not doing that one. Just going to use this. Okay. I'm just saying this is 120. Okay, it's not factually. I mean, visually it's probably a little bit close to 125. So this is your SCO3, and then you have sulfate. Sulfate, how much? 97.9. So if you add 120 plus 97.9, let's say you add 120 plus another 100, so 220, and then 97.9. So this will 217.9, right? 217.9. So let's see, this is 218. So let's go up to here. And so that would be your sulfate. Okay. So let's write. I mean, what is total hardness? Total hardness is basically calcium plus magnesium. So this is total hardness. Okay. And then carbonate hardness is basically whatever the amount carbonate is there, as long as less than total hardness. So this is carbonate hardness. And then everything before total hardness has to be non-carbonate hardness. Okay. But now question is, it says what is the calcium CaCO3? So now how do? You basically match them. You have calcium above, and you have calcium here. You have SCO3. Just match where it intersect. Below that would be calcium. So that means all SCO3 is, because total SCO3 120, but if you see calcium, it's all the way 125. So you have more calcium. That means there is all SCO3 is occupied by calcium, but some calcium remain that goes to sulfate. So that means another way you can write here is this is carbonate hardness is actually your CaSCO3. Okay, because all of those are there. So that means this is equal to 120 milligram per liter. Then as you can see, 120 to 125. So this is 120, this is 125. So this range is basically another 5. Okay. Just going to write it here so that you can see that this is 5 milligram per liter is your calcium sulfate. Because that little extra, that your calcium, there are a little more calcium than SCO3. So that extra goes to sulfate, that intersection. And then, as you can see, if you intersect magnesium, 5 is gone from sulfate, and magnesium is completely within that sulfate layer. So that means all the magnesium is stay as magnesium sulfate. Okay. So that means you can write this one. This entire section is magnesium sulfate. Because there is no magnesium that goes to a carbonate, it's all taken by calcium. And there is just enough sulfate to cover entire magnesium. Sulfate is going beyond that. There is nothing else. So you can write. So this is same as SCO3. This is basically, you can write, how do you get that one? It's basically calcium, total calcium minus the SCO3. If you want to write the formula. Visually you can write that, or just directly, or you can write that. That's how we get it. So that means your magnesium, that means calcium sulfate. So you write calcium sulfate equal to that. And magnesium SCO3, what's that amount? Is there any magnesium associated with carbonate? Because as you see, all carbonate is occupied by calcium here. There is nothing left for magnesium. So this MgCO2 is 0. What about, so you did calcium sulfate. How much is magnesium sulfate? That's equal to, so MgSO4 is same as total magnesium, which is, you already calculated, it's 82.3 milligram per liter as CaCO3. So if I state your assumption, right? So that's, if you just visually show that, that's is just there. But if you write as equations like this, then you can write your assumption saying that all magnesiums are basically bound to sulfate because all carbonate has gone with calcium. That's your 2 point. Okay, so I'm going to write the next of them is I'm going to write the formula because you have 2 minutes remaining for this class. Because all you have to do is write the formula and get the answer, right? So the question was how much CaO required. So a lot of times you calculate CaO is same as CaOH. Okay. As far as concentrations, okay, because they are equivalent. Because if you see CaOH is produced by CaO plus H2O. So this is true if it is milligram per liter as CaCO3. Okay, so the units are different. Unit are same. That's why I wrote it. But if you have to write as a milligram per liter as CaO, then you have to convert them from calcium carbonate to that. So let me get to that. So how do you know how much CaO? Okay. Basically CaOH so this is a CO2, yes. Okay. So if you are changing as CaOH, so let me write now two formulas so that way you know. If you do that one, you basically do this. Okay. If you want to measure the concentration as convert from CaCO3, you just change it to as molecular weight because both are equivalent. Okay. Or another way to say is equivalent weight of CaCO3 and equivalent weight of this. That's the right formula. Because both are same molarity, that's why you keep as molecular weight. And once you know the concentration as CaOH, you can also measure the concentration as CaO. It's basically CaO concentration is CaOH concentrations, molecular weight of CaO divided by molecular weight of CaOH. Okay. The same way, just as equivalent. But now the formula is how do you write CaOH concentrations? That's the one that is critical, right? So I'm just going to write it here. CaOH concentrations based on that formula that you have in the, okay, let me see in the total formula. So CaOH formula is CO2 plus CaOH SCO3 plus 2 magnesium SCO3. Then you have magnesium non-carbonate hardness. Okay, so that's basically in this case it's going to be magnesium sulfate. This is Mg2 plus Mc non-carbonate hardness. Okay, any magnesium formula. And all the numbers are you already calculated. So you just plug the value, you can get the answer. So this will be CO2 is 13.6 plus 120 plus this is 0. This is 82.3. It's going to be 15.9 milligram per liter as calcium carbonate. So same thing, next formula, just going to write it here. Na2CO3 is basically sum of all non-carbonate hardness. Non-carbonate hardness. So in this case, calcium non-carbonate hardness is CaSO4. Magnesium non-carbonate hardness is MgSO4. And you know this one is 0. Oh no, this one is 5. This one is 82.3. I'm going to write the formula for other two, then you can leave. I mean, you can leave now if you want to. I'm just going to complete it. Then you have CaCO3. Formula is CO2. CO2 is producing that, 2 CaSCO3, 2 MgSCO3, 2 plus CaSO4, non-carbonate hardness. And then you put all this value and get the answer. The last one is if the pH of the groundwater increases, then would it more or less expensive? If pH increases, that means you have more OH. Okay. And the reason how carbonate hardness, if you see, you need to increase the pH to precipitate stuff, right? Because if you see magnesium hydroxide, to precipitate, you need a lot of OH. And those OH come from lime, CaOH, right? So that means you have to use less lime. If more OH, less lime needed. The lime is basically CaOH. That's what you are adding, right? So the whole reason you are adding lime is because not because calcium, but OH. If your OH is already high, then you don't need much. Less expensive. Okay, well, at least we solve one question. See the another question next week. Solve this one. I'll solve another 2 questions next week. Okay, so that's good.